Watch the same fluid in the same pipe. When it moves slowly, the flow is smooth and orderly. Speed it up, and it breaks into a churning, chaotic wake. Same equation, two completely different worlds, and one single number decides which one you get. The Reynolds number. Here's the plan. We start from the full law of motion for a fluid. We find the two forces fighting inside it. Their ratio is the Reynolds number. Then we watch the equation itself simplify at small and at large Reynolds. This is the equation we built over the last few videos. On the left, mass times acceleration. On the right, the forces that push the fluid around. Let's label each piece just to recap. The whole left side is inertia. On the right, the pressure push, the viscous friction, and gravity. Today, only two of these decide the flow. First, inertia, the fluid's tendency to barrel ahead, and viscous friction, the fluid dragging on itself, ironing differences out. Inertia is like a heavy truck. Once it is moving, it wants to keep going. Viscosity is the sticky friction between layers, pulling neighbors along and ironing out any sharp change. Whether the flow stays smooth or tears apart comes down to which of these two wins. So let's measure how big each term is. Call the flow speed u and the size of the object L. A derivative is a change over a distance, so it roughly divides by L. Start with inertia. The velocity is about u. The gradient of velocity divides by L, so it is about u over L. Multiply them, and inertia comes out around rho times u squared over L. The viscous term has two derivatives, so it divides by L twice, by L squared, times the speed, u, that gives mu times u over L squared. Now divide inertia by viscous. Almost everything cancels, and what is left is rho ul over mu. That ratio is the Reynolds number. So Reynolds is just a score. When it is small, friction wins, and the flow is smooth and laminar. When it is large, inertia wins, and the flow goes turbulent. Honey oozing is almost zero. Water in a pipe, a few thousand. A car or a plane, in the millions. Now, back to the equation. At small Reynolds, the inertia term is tiny, so we simply drop it. What is left is a balance of pressure and friction alone. This is creeping flow. Think honey, or a bacterium swimming, so dominated by friction that it is even reversible. At large Reynolds, it is the other way around. The viscous term is negligible across most of the flow, so it nearly vanishes. It survives only in a thin layer right at the surface. Inertia rules, and the wake breaks into turbulence. So the Reynolds number is one number that tells you which terms of the full equation actually matter. Small, and friction smooths everything. Large, and inertia takes over. Same law, two worlds. That's all for this video.